we're going to start with a recap of what the different radiations are so that we can understand how a radioactive isotope is affected when either alpha, beta or gamma radiation is emitted. An alpha particle is usually written like that with a 4 and a 2. So it's made up of 2 protons and 2 neutrons, often referred to as a helium nucleus, because it is basically a helium atom without the electrons. So it has a mass of 4. Then we have a beta particle, which has a -1 charge and is given an approximate mass of 0, even though it's roughly a relative mass of 1/1860. For the purposes of writing these simplified decay equations, it's given a mass of 0. And it's referred to as a fast moving electron, hence the -1 charge. And then finally is gamma radiation. So gamma rays are electromagnetic waves, and for the purposes of these simplified decay equations, they have 0 mass and 0 charge. So when a radioactive isotope decays and gamma is emitted, if it's just gamma, the nucleus will not be affected in terms of the numbers. So these equations here just summarize what happens to the nucleus of a radioactive isotope when an alpha particle is given out and when a beta particle is given out. So the only thing to remember is with a beta particle, the way that it's formed, so if I just highlight this using a different color, the way that a beta particle is formed is that a neutron in the nucleus basically turns into a proton, which then stays in the nucleus, and then also an electron is produced, and that is ejected, in other words, kicked out. And when it's ejected, this fast moving electron, that's what we refer to as a beta particle. Now, for an alpha particle being released, it has a mass of 4, and it's just emitted from the nucleus in one go. So what you'd expect is the overall mass of the isotope to decrease by 4, and then because the alpha particle has 2 protons, you'd also expect the atomic number to decrease by 2 as well. As mentioned previously, with a gamma decay, the nucleus is unaffected. So let's get into it and take a look at what is going on here. So in the first one, we have 2 examples of an alpha decay. So we have uranium-238 has decayed to uranium-234, and an alpha particle has been given out, which is now being expressed as a helium nucleus, so this one. So immediately I can put in the numbers 4 and 2, and I can work backwards to work out the atomic number of the uranium isotope. So if I add 2 back onto 90, that gives me 92. Then the next one is radium rather, and that is turning into Rn. And again, by an alpha decay, so I can put in the numbers for the alpha particle and work backwards to work out what the mass is. So because an alpha particle has an overall mass of 4, I need to add that back on, and that gives 2, 2, 2. Right, let's move now to a beta decay. So with a beta decay, because a neutron turns into a proton, that is why the atomic number has gone from 53 to 54. However, because a beta particle is given an approximate mass of 0, therefore the top number does not change. So that goes in as 131. Or another way of thinking about it is to remember that a proton has a relative mass of 1 and a neutron has a relative mass of 1. Okay, so the same relative mass. So if a proton is being made, it's gone from 53 to 54, and that's because a neutron has turned into a proton. The way to think about it is that the neutron number goes down by 1, but then the proton number goes up by 1. So overall, this top number remains unchanged. Right, finally, we have an element Tc technetium. And for this, you're going to need your periodic table, where we can work out what it's going to transform into, say, for both an alpha decay and a beta decay. So let's take a look at that. So one of the radioactive isotopes of technetium is technetium-99. And let's just say in the first instance, it undergoes a beta decay. So we can write beta 0, -1, and then it's going to turn into something which has an atomic number of 44, and the mass number stays the same at 99. So what is 44? Well, I have my periodic table next to me, and if you look at the element next to it, it's Ru, which is ruthenium. Now let's just say this one also undergoes a decay. And the reason why that it might undergo a decay is because isotopes tend to be radioactive when the mass number differs to the one that you see in the periodic table. So ruthenium in the periodic table has a mass number of 101 and then 44. And the mass number is obviously influenced by the number of neutrons. So if a nucleus has more or less neutrons than the most stable isotope, then it tends to be radioactive. So generally, more neutrons than the most stable isotope makes it radioactive. So let's just say for this last one, decays by, say, an alpha this time. So we write either He or alpha. It depends. In the question, it would tell you. So let's just stick with He, as that's what we've seen so far. And we put 4 and 2. So as that particle has been kicked out of the nucleus, the top number is going to decrease by 4. So that takes us to 95. And the bottom number is going to decrease by 2 because the proton number has decreased by 2. So now we're left with 42. And if we look at the periodic table, we can see that the element with an atomic number of 42 is molybdenum. That's it. So if you have any questions, please comment down below. Otherwise, I would see you in the next one.